I just wanted to first thank you for inviting me to speak today, and thank all of you for coming. My name is Andrew Dotson. I'm a graduate student at New Mexico State University. I can't ever make a decision on what PowerPoint templates to use, so I just used my school's. And today I'm going to be giving a talk on my unorthodox approach to science communication. So let's go ahead and get into it. So a bit of background about myself. I'm in grad school. I'm doing research in theoretical nuclear and particle physics. This is more or less how my mom sees me versus how my research advisor sees me, scared, alone, and I don't know how to use a hammer. And I'm going to talk a little bit later about what got me into physics and things like that. But once I did make that decision, I knew that for me, it was theoretical physics or nothing. Not particularly good with my hands. I've enjoyed the experimental physics classes that I've taken, but it's just not for me. Now, my understanding is that there aren't typically many nuclear particle physics talks given here, or at least there haven't been too many, if I understand correctly. So I thought I'd give a little bit of a primer of what it is that we do or what I do. So for nuclear and particle physics, what's exactly on the roster? So you may have seen this picture before. The building blocks, the Legos of the universe, are described by what's called the standard model of particle physics. By the way, I'm going to be taking sips of water throughout this talk. I recently had COVID, and though I'm not contagious anymore, my voice still isn't back to where it used to be. So just forgive me for those kinds of breaks in between. But the building blocks of the universe are described by the standard model of particle physics. We've got the quarks, which are the particles that interact via the strong force or the strong interaction. We've also got the leptons, which are elementary particles that do not interact via the strong force. The famous example being the electron, then we've got its heavier cousins, and then the corresponding neutrinos. How are these forces communicated? Well, they exchange the force carriers, which are the gauge bosons. Everyone's heard of photons. The gluon is responsible for mediating the strong interaction, the strong nuclear force. And then we've got the W and Z bosons for the weak nuclear force. And then the famous Higgs boson, of course, it completes the puzzle. You may have heard of the Higgs boson as being responsible for giving mass to particles. It's a bit misleading of a statement because most of your mass does not actually come from the Higgs boson. It gives mass to these guys. But if we form composite particles that are made up of, say, quarks or leptons, most of their mass typically is not from the masses of its constituents. It comes from the binding energy or the energy of motion that tends to contribute a lot more to the overall mass. That's a bit of an aside. But the dynamics of all of these elementary particles is contained in a very simple equation referred to as the standard model Lagrangian. For those of you who are not familiar with this, let's go ahead and go through each term individually and explain what they mean. So this term, I'm just kidding. This is a horribly long and complicated equation. It could be written in a much more concise way, but I just wanted to scare you. So that's the standard model of Lagrangian. It's all there. The one thing that's missing from this, of course, is gravity. We don't have a full quantum field theory of gravity that could be appended to the standard model, at least not one that everyone agrees on. So that's to be continued. So I mentioned that we can form composite particles of all of these particles. If we say form a bound state of a certain combination of up quarks and down quarks, that becomes what we call the proton or the neutron, collectively just referred to as the nucleon. So I could be referring to one or the other. So the up quark has, in units of the electron charge, a charge of 2/3, the down quark a charge of -1/3. So if we say that the proton is made up of 2 up quarks and 1 down quark, then we get 2/3 plus 2/3 minus 1/3. You get +1/3. That's the charge of the proton. So we like to think of the proton as being made up of 2 up quarks and 1 down quark. In reality, it's not that simple. Gluons, these are quarks. They communicate by exchanging gluons because they interact strongly. And these gluons can split into quark-anti-quark pairs, popping in and out as well. So one thing that we can ask is, how do properties of the proton emerge from properties of its constituents, properties of the parts that make it up, like the quarks and the gluons? referring to the parts that make up the proton or the neutron. They were cleverly also named partons. So those could be referring to quarks or gluons. And that terminology was coined by Richard Feynman. This information, though, of these properties of the quarks, the gluons, or of the proton itself, this stuff is encoded in what we call parton distribution functions, as well as these other objects called form factors. And which ones we talk about depends on the nature of the experiments that we're conducting or that we're interested in. So what kind of experiments am I talking about? It's always scattering experiments. So here we have an electron coming in with a certain momentum, a proton coming in with a certain momentum. They communicate with each other electromagnetically, so that means they exchange a photon. That's what this squiggly line is. And depending on how the energy of the experiment, it may be high enough energy to where we break the target apart, break the proton apart, which are these lines out here, these jets. And when we break the target apart, that's what's called inelastic scattering. And if it leaves it intact, maybe it's at a lower energy and the proton just scatters but stays intact, that's what we call elastic scattering. And depending on which experiments we're running, that tells us which one of those particular buzzwords that I threw at you a minute ago we're interested in. So parton distribution functions are typically of interest when we break the target apart. And what they do, at the higher energies, we're really resolving the proton. We're seeing what's inside. So when this photon gets exchanged and it scatters off the proton, in reality, it's hitting one of the parts that's making up the proton, one of the quarks or maybe the gluon or whatever. So the parton distribution functions, one way of interpreting it is it tells you what fraction of the total proton momentum was carried by the quark that it struck. Okay, so in a sense, it gives you this notion of how momentum is distributed inside of the proton. If we leave the target intact, we can talk about form factors, which come from symmetries of the theory. Now, I understand maybe there are some upper years in the audience. You may have learned that symmetries lead to conservation laws. It's from Noether's theorem. And when you have these conserved quantities from symmetries and we're leaving the target intact, we found out that we can relate these conserved quantities, they're called conserved currents, to fundamental properties of the particles that we're hitting and relate them to densities like charge densities, magnetic moments, angular momentum, things like that. So those are the big things. These are the big objects that we are both interested in from a theoretical standpoint and experimentally. And it all comes down to scattering experiments. So if we do scatter an electron off of a proton, we could ask, for a given proton momentum, what fraction of that momentum is carried by the struck quark? Well, if the proton was just made up of 3 quarks, a reasonable guess would be that the quark you hit carries about 1/3 of the total momentum. If we plot the distribution of this is the plot of the parton distributions, we see that for this blue line here, which is the momentum fraction of the up quark, if we strike an up quark, we see that it doesn't peak at about 1/3. It peaks at about 0.2 and less for the down quarks, and the other quarks look a little bit different, but that's because we typically don't see too much representation of the other quarks for the proton. But what I'm getting at is we see it peaked at significantly less than 1/3. How are we to interpret that? Well, what it means is there's more stuff going on inside the proton than just those 3 quarks. It means that there's other things inside there that are sharing some of that momentum, which brings the momentum that the quark has down from 1/3 to a bit less. So even a simple question like how is momentum distributed inside of the proton actually has a pretty non-trivial answer. So we call the 3 quarks that we think of whenever we talk about the proton or the neutron the valence quarks, but we now understand that there can be a sea of other stuff going on inside of the proton as well, which is pretty fascinating. And this stuff has to be accounted for if you want to make a prediction that is consistent with reality. But there's a lot more properties to matter than just its momentum. Right, we've got charge, spin, I should say orbital angular momentum, linear momentum, mass, magnetic moments. Is there anything else? Well, it turns out that there is one more property of matter that doesn't really get the attention that it should. If this property of matter was a particle, it would be called the lepton, because people don't really discuss it as much as I think that they should. It doesn't even have a cool name, frankly. It's just called the D term. Now, this property of matter we don't truly understand, and part of the reason it hasn't been given so much attention is because it's incredibly difficult to access information about it, both theoretically using pen and paper and experimentally in these scattering experiments. I'm hearing a little bit of feedback on my end. Is that happening on anyone else?
Yeah, I hear that too. Someone's mic may be on. Let me check. It's
Okay,
good
cool.
now.
Awesome. It was a good drink break time. So it's hard to access both experimentally and theoretically. But what does it mean? Well, in relatively recent years, people have found out how to relate this guy to something called the energy momentum tensor. This is a huge object of interest in my own research. I've given entire talks on just that one thing alone. Now is probably not the setting to delve into that too much, but it's relatively self-explanatory. It describes energy and momentum distributions, among other things, of the particles. And people have learned that this D term is intimately related to this energy momentum tensor. And based on how it's related, it's been discovered that somehow it's correlated to how pressure is distributed within the nucleon, but it's not quite clear how. This is, as we see here, 2018. This is pretty new stuff. So where I come in, and I'm not going to talk much more about this stuff. I just wanted to give a little bit of a primer on my research and where we're at. My research involves calculating this D term in different models. If you want to describe nature, you have to have a model in mind. And the goal is to one day really provide that formal link from the D term to pressure distributions. If you've had upper division E&M and you talk about scattering, you may learn that there's something, if you're scattering off of a point-like or a composite particle, there's this form factor that is related to the cross-section. And it turns out that for E&M, in classical E&M, this form factor is just the Fourier transform of the charge distribution. So we have this direct link between this abstract quantity, the form factor, and a density that you can actually measure, or something that you can maybe look up in the particle data group booklet or something like that. Now, I do these calculations in quantum field theory, and one has to be much more careful when relating these form factors to physical observables. And luckily, we are able to do that for things like charge distributions, magnetic moments. But how to do it for pressure, no one knows how to do that yet. Among other things, spin is another big thing that no one knows how to describe how it's distributed inside of the proton. One of the main applications, as far as theoretical physics goes, it would be applicable to a theorist, I should say, is that understanding the D term would allow us to know if the models we're using to describe nature are even stable in the first place. Is the particle that we're describing could it actually exist? So with that being said, I'm going to leave the research part of the talk with that. If people have questions on it later, I'd be happy to delve into a little bit more. But now we're going to kind of change gears completely. So I talked about I'm a grad student kind of thing. I also make physics videos on YouTube, also by day. I've been doing this for coming up on 4 years now. And so for the rest of this talk, I wanted to share kind of why I started what I think is one of the more niche channels on YouTube and why I think it works. So to start off, when it comes to science communication, there's no shortage of the popularizers that talk about those really big topics in physics. They talk about black holes, wormholes, time travel, string theory, all of those big things that they reel prospective physics students in. They do a good job with that. I know it worked on me. But I think it can give the wrong impression of what studying physics is actually like. You may go into your first year thinking day one, you'll be tackling, okay, how exactly do we unify GR with quantum mechanics? But, asking you all now, is that what you learn in any of your physics classes? I think the answer is going to be no. No, your life in your first year physics is all about friction and tension And if your professor's feeling particularly crazy, maybe you'll do some air resistance. Now, so the goal of this talk, the rest of this talk, is not to convince you that these popular science topics need to work their way into the physics classroom more, but rather that I think there needs to be a bit more exposition on what studying physics actually is like. And not in a way that's just describing the courses that you'll be taking, but also sharing the overall experiences. Oh, is someone saying something? Oh, I think someone's mic is on again.
Yeah, they're just eating. I muted them.
Okay, no problem. Now, the best way that I think this stuff can be communicated is through YouTube. So I think I'd like to talk a little bit about why I started my channel and kind of the direction that it's headed over time. So I didn't initially start as a physics major. I started off in biology. I wanted to be a medical doctor, and if you want to be a doctor, you cross off a lot of those requirements by studying biology. And I can only speak from my own personal experiences. People experience things differently, sure. But for me, it seemed like a lot of memorizing cycles, and this is what this is called, and this is what this is called. And you could ace exams not by understanding things, but just memorizing. When I took organic chemistry, that's all it was memorizing mechanisms, and there didn't seem to be too much depth to it, or at least there wasn't really that big of an attempt to make deeper connections. And it was around this time that I came across a physicist named Richard Feynman, and I'd like to share a little bit of a video of him. Now, actually, does Microsoft Teams share the audio as well? If you can't hear this, let me know if you can't. Can you hear this?
I don't think so, no.
Okay, so let me end this real quick and make sure, let's see. I'm going to just stop sharing real quick and try to start sharing and make sure that it shares the audio. I think there's an option. Yeah, include computer sound. So now we should be good to go. Sorry about that. And let me know if you hear it now.
We can hear it.
Cool. Oops. I need to stop clicking things.
Feynman is in the forefront of one of the oldest and most intriguing games of hide-and-seek in science, finding the ultimate constituents of the world. In this search, Feynman is a celebrated maverick who is encouraged by his father, a New York clothing salesman, to confront conventional wisdom.
One Sunday, all the kids were all walking in little parties with their fathers in the woods. Then the next Monday, we were playing in a field, and the kid said to me, "Say, what's that bird? What's the name of it? You know the name of that bird?" I says, "I haven't the slightest idea." He said, "Well, it's a brown-throated thrush." He says, "Your father doesn't teach you anything." But my father had already taught me about the names of birds. We walked and he says, "That's a brown-throated thrush." He says, "Know what the name of that bird? It's a brown-throated thrush. In German, it's called a Flügelflögel. In Chinese, it's called a Qinglongtong. In Japanese, a Tohatahara, and so on. And when you know all the names in every language of that bird, you know nothing, but absolutely nothing about the bird. Then we would go on and talk about the pecking and the feathers. So I had learned already that names don't constitute knowledge. It's knowing the name of something. That's caused me a certain trouble since, because I refuse to learn the name of anything. So when someone comes in and says, "You got any explanation for the Fitz-Clonan experiment?" I says, what's that? He says, "You know, that the long-lived K meson disintegrates into 2 pi's. Oh, yes, now I know. But I never know the names of things. What he forgot to tell me was that knowing the names of things is useful if you want to talk to somebody else. So you tell him what you're talking about.
I love that clip. So the main takeaway, names don't constitute knowledge. If you don't know about Richard Feynman, you will. There's so many amazing videos of him on on YouTube, interviews with him explaining things like this one here. You should really check him out if you don't know about him yet. But that really resonated with me. Names don't constitute knowledge. And I remember going home one year on break and talking with my dad, and I was probably talking about like string theory and black holes, these things that I saw on Cosmos or Into the Universe with Stephen Hawking, rest in peace. And my dad mentioned that when I come home, I'm never talking about biology. I'm never talking about the cell cycle or things like that. I'm always talking about these crazy theories or things that I saw on TV. This is probably more or less my response. But he had a really good point. He said that it doesn't seem like my heart is really in biology. It's not the thing that I enjoy talking about. I enjoyed talking about physics, and for me, physics has always just seemed more self-contained and satisfying. It's the more fundamental. The question eventually leads to physics always. It's what turned chemistry into a science when during the advent of quantum mechanics, and then chemistry, biology, and so on. And maybe one day psychology will even be a science. Just kidding, by the way. But after thinking about it for a while, I realized my dad was right, that I should be doing physics instead of biology. The school that I was attending had a medical school kind of attached to it, so it made sense to go there. But if I wasn't going to be a medical doctor anymore, if I wanted to do physics instead, you know, I could just as well go back to my local four-year university. So that's what I did. And I switched my major to physics, and I wanted to get a bit of an idea of what to expect. So what did I do? I went to YouTube, and I started looking, what is studying physics like? What is it like being a physics major? And I came across a YouTuber named Simon Clark, and he would make these videos that was showing his experience studying physics at Oxford University. And it was really useful and insightful because physics, for the most part, is universal. I like to think the people at Oxford don't get access to the secret laws of physics while the rest of us are stuck learning Newton's laws. I figured it translated well, but I couldn't help but have the suspicion that your overall experience really depended on the school you went to. And what is it like if you're not someone who goes to Oxford, but you go to a regular old four-year university? And I couldn't really find the answer to that. There wasn't much out there. I think the experience would depend wildly. I wasn't someone who could get into Oxford, but I did go to a nice four-year university with approachable professors and a nice society of physics students that made the overall experience much more enjoyable. And I thought maybe that there were other people out there that would need to see that. And I thought, well, I could do that. I could start making videos of that. I think someone once in my comment section called me the poor man Simon Clark, and I couldn't think of a better description than that. I thought that was pretty funny. So that's what I did. I started recording myself going to and coming from classes. I talk about the courses I enjoyed and ones that were giving me a run for my money, doing things with SPS. And it was great. They weren't very good videos. I didn't know what I was doing, but they were really honest. And I really enjoyed making those kinds of videos. 1 second. So I didn't know it at the time, but the primary videos that I were making were vlogs. That's kind of the style of video that I was making. And I enjoyed doing this. I enjoyed talking about what I was learning, but it got to the point where if I brought up something that I was learning, the Clebsch-Gordon coefficients, I'd want to be able to explain it in some way so that I'm not just throwing buzzwords and jargon out there. But if you're doing a vlog, which is more of a story, it's not really the setting to have this 10-minute tangent describing like direct product spaces and things like that. That's not for that. So that got to me exploring a different kind of video format, which were just video lectures. They were videos where I could be as thorough in an explanation as I would want them to be if I were looking up the kind of video. So this was an example of me just converting Maxwell's equations from differential to integral form. And I still do these to this day. They just became a bit more involved. So now I do things like I have a series of tensor calculus for physics. So it's still the same style, but just more involved concepts. So that's the second kind of video that I started making. While I was doing it, though, I didn't know that these were the styles that I was doing. It's just after the fact, from self-reflection, it was like, oh, this is where I started experimenting with that style more. But when I first started out, I only had 2 subscribers. I had my mom and my best friend. And I kind of insisted on it being this way. I didn't tell my other friends that I had a YouTube channel or my family, because I wanted to make sure that the people who were subscribed were there because they were really interested in what studying physics entailed. And if you only have 2 subscribers, it's very hard to find your channel. So I knew that the day that my subscriber count went from 2 to 3, someone did some digging, and that told me that there was a booming market for talking about physics, apparently. I knew I was in business, which was pretty exciting. Vlogs are nothing new. Lectures on YouTube are nothing new. Everyone knows about things like Khan Academy. My first kind of new style of video was I wanted to show kind of the lighter side of physics. So I got together a bunch of my friends from SPS, and we wrote a bunch of physics one-liners, original physics jokes, because I was tired of hearing neutron walks into the bar, the bartender says no charge a million times. So we wrote a bunch of physics jokes, and we made a video together, If You Laugh, You Lose, physics edition. And my channel started to gain a lot of traction from these kinds of more comedic videos, because apparently there's a market for physics-based comedy. Who knew? Towards the end of this year, though, my first year of making these videos, I did some cataloging, or some inventory, I should say, and I realized that I only made about 25 videos my first year of actually making videos. And my kind of excuse for doing this was, oh, I wanted to give myself more time, that way I could make a better video, which was absolute BS, because I didn't have the skill set. If I gave myself more time, I wouldn't know what to do with it. And I really wanted to develop that skill set a bit farther, or a lot more. And I thought the only way to do that was to start making as many videos as possible. So I decided to try something. I would make a new video every single day, no matter what, until, well, for as long as I could. And kind of in that process, I would learn more about what kinds of videos I enjoyed making, and I would further develop that skill set of editing. That way and storytelling. That way, if I did give myself more time to make a video, I could actually make it better in doing so. And someone once told me, it might have actually been Simon Clark, I don't remember, that your first 50 videos are going to be bad. That's your experimenting phase. You're just trying stuff and seeing what works and seeing what you like making. So it's nice to get those out of the way, I guess, as fast as possible. And the cool thing is, during that time, no one's really watching your videos anyway, because you're new and it's hard to find your videos. So that experimenting phase, it's kind of low consequence. If you make a bad video, who cares? Only my mom saw it anyways. So that was pretty nice. But what started out as like this means of developing the skills to make better videos eventually sort of became my thing. My thing on YouTube was making videos every day about physics. I kind of lost the whole theme. So at this time, again, I still didn't know that I was doing vlogs, comedic videos, and lectures. And at this time, I kind of lost that a little bit, because it's really difficult to make a video every single day. Sometimes you just don't know what to talk about. So here there's like talking about physics books or doing a physics history quiz, things like that. But so it wasn't so much my thing anymore, vlogs, lectures, and skits, but rather just having something for you to watch every day, no matter what. And aside from the days that had to do with me moving for grad school, I can count on about one hand how many times I missed a daily upload, and there was a grand total of 314 that I made. And then, speaking of grad school, I didn't get into my PhD program right away. I was rejected, and I decided to take kind of a big risk and move across the country anyways to pay to take classes at a school I didn't get into, in hopes that ball in their court, I could prove to them that I had what it took. But that kind of thing costs money. And at the time I had about 8,000 subscribers, I think. And I decided to put out a post on my channel that said that I would be offering Skype tutoring. And just enough people signed up for that to where I could barely scrape by my first semester of grad school. So that's something I'll always remember and be thankful for. Making videos every day gave me an audience that was kind of like there for me when things weren't going too well. So that's pretty big for me. The next semester, I reapplied for grad school, and thankfully I got in. So now that I was actually in grad school, I made a video like reading my grad school rejection letters and things like that. And so the first year that I started making these videos, I went from took me a year to reach 1,000 subscribers, which isn't very good at all. The second year, I reached 10,000 subscribers. So I had this idea of, I knew what happened if I kept doing the daily uploads. It was working for my channel. But now that I was accepted into grad school, I knew that I would have to take on TA responsibilities on top of my graduate courses and start doing research. Making daily uploads just wasn't feasible anymore. But I knew what happened if I kept doing it. I had no idea what happens when I stop, and that was kind of scary for me. But I knew that I had to do it anyways. I stopped making daily uploads, and this was like the time to test, did I really learn how to edit better, tell a better story, put together ideas in a more enjoyable way. And that third year that I stopped making my daily uploads, my channel went from 10,000 to 100,000 subscribers. So it seemed to be paying off a bit. So yeah, my 314th daily upload was just reading comments. Very, very original. But now that I graduated undergrad, after I stopped making my daily uploads, I did some self-reflection to be like, well, what did I learn? What kind of videos do I enjoy making? And I learned that it was those vlogs, comedic, and lectures. Now that I was in grad school, they all kind of changed a bit, but they were kind of the same in the same sense. So for vlogs, instead of talking about what I was going through in undergrad, that got into vlogging about doing a PhD in physics. And then the comedic videos, I started doing more involved skits, but the acting is still equally as terrible. And for the lectures, instead of deriving the kinematic equations as an example, I would derive, say, the Feynman path integral or something. The lectures always do, as far as views go, they do much worse view-wise than all of the other videos, but I think that those are probably my favorites to make, so I do them anyways. And at first glance, these all seem like wildly different formats, but I think that they all kind of achieve the same thing. In their own way, they let students know what's around the corner. You know, some people want to watch a story unfold, so they watch the vlogs, or some people, I'll get comments, they just want to laugh at the end of the day, so they watch the skits, or some people are masochists like myself and do want to watch lectures, so they watch the derivation videos. And the crazy thing about this stuff is that the people do seem to want more. For the skit stuff, you know, I'll get comments of people who say they don't get the jokes, but they can't wait until they do. And it's the exact same for the heavier derivation videos. Comments like, I don't know what he's talking about, but I want to know one day. The equations look really cool. It's an excitement of like one day being able to understand this stuff. And I think that means that this stuff is worth exploring more. You don't have to just explain the pop science stuff to get students interested. You just have to be a little bit creative with it. So this stuff is worth exploring more, definitely. And I'm in grad school now. This was a selfie I took last week. I can't share any new undergraduate experiences, but I know a lot of you in the call right now definitely could. And the same goes for grad students. When I finish my PhD, I'll be looking to YouTube to see what doing postdocs are like, or what being a professor is like. And just overall sharing your experiences is just so valuable. I've said it a million times that I went through my academic career with certain opportunities and privilege that other people just don't have. And if you just listen to my perspective, it'll give you a very skewed point of view of what studying physics is actually like. So it's incredibly important that those other perspectives be shared. And I encourage you all to be part of that. There's this new generation that is interested in whatever the hell it is that you do. And so I hope I've convinced some of you to maybe hop on board and start making some videos. I'll definitely check them out if you do. And I really appreciate you taking some time out of your day to listen to me talk about this stuff. And that concludes all that I really had to say. So thank you.